Hello everyone, this is Dr. Lennon and we're going to go over the test 1 review. So this test covers chapter 5, so we're looking at essentially the topics of integration from Riemann sums through basic antiderivative techniques, average value and net change, and then integration by substitution as well as integration by parts. So this first one is going to be a Riemann sum estimate. So let's say estimate the area below f of x equals the natural log of x from x equals 8 to x equals 12 using let's do two parts. Let's say A, 5 left rectangles, and then the second part will just be using 5 right triangles. So for both parts, the first thing we want to do is compute the width of the rectangle, so that's delta x here. So you can do the length of the interval, 12 minus 8, divided by the number of rectangles you want to use, which is 0.8. And then you want to make your interval. So basically, remember, we're starting at the lower number up here, x equals 8, and then we're just counting up by steps of 0.8 until we get to 12. So we have 8, 8.8, 9.6, 10.4, 11.2, and then our last number, 12. And really what's going on is we have a graph above this somewhere, and we're just using the left-hand corners to touch the function. So the formula here, as you may recall, we take our width and then we plug each of those numbers. The first, so for the left, we're going to use the first 5. So this is going to be for the left. And then for the right, we're going to use the last 5. So we don't use that number 12 when we're doing the left-hand sum. So it's going to be 0.8 times the natural log of 8 plus the natural log of 8.8 plus the natural log of 9.6 plus the natural log of 10.4 plus the natural log of 11.2. And from there you can just plug that into your calculator and estimate that using 2 decimal places. So that comes out to 9.02. Okay, so for B we're going to do the same thing, but we're going to be using the 5 right rectangles. So here the area, same delta x, same intervals, but what we're going to do is we're not going to use the 8 and we're going to use the 12 instead for the right. So our area here is pretty much the same formula, but we're starting at natural log of 8.8 and finishing at natural log of 12. So plus the natural log of 9.6 plus the natural log of 10.4 plus the natural log of 11.2 plus the natural log of 12. And this one, the right rectangle, comes out to 9.34. So that means the left rectangles were an underestimate of the true value of the area, and the right rectangles were an overestimate. The true number is going to be somewhere in between. Okay, so for number 2, what we want to do is we just want to look at a picture. So we'll say find the value of each integral from the graph. So this is just checking your understanding of the new notation for the integral. So let's say we have, a graph where we have some parts, and okay, maybe this has area 5, this has area of say 2, and this has an area of 4, and maybe this is point A, this is point B, this is point C, and this is point D. So we'll just go through a handful of these. So let's say A, we want to find the integral from A to C, and we'll call this f of x, this function. of f of x dx. Well, we're just checking that as you go from left to right, the numbers above the x-axis are positive, and below they're going to be negative. So this is just an arrow pointing to the area between b and c is 2, but it's below the x-axis. So the bottom number indicates where you start. So we're starting at A and we're finishing at C, and going from left to right. The bottom number is the starting place, and the top number is the finishing place. So that's how you know we're going from left to right. So 5 is positive in that direction, and the 2 is negative. So 5 minus 2 comes out to 3. Let's say B, we were doing the integral of, say, let's say we start at, sorry, this D kind of looks like an A. This is a D. Let's say now we start at D and we go to B of f of x dx. So now you can see the starting thing is furthest most to the right, and we're going, and B is to the left of it. So we're starting at the right and going to the left. So that means the typical conventions are going to be the opposite of what they normally are. So going from left to right, the 4, which is normally positive, would now be negative, and the 2, which below would be negative, now becomes a positive. So negative 4 plus 2, this would come out to negative 2. And maybe we'll just do one last one, say part C. Say we did the whole graph, just say we started at A and finished at D of f of x dx. What would this give us? Well, this is just adding them all from left to right with the normal convention. So 5 minus 2 plus 4. So that comes out to 7. So that's just kind of reading the graph using the new notation, not really doing any math. You just have to make sure you understand that the general orientation for above and below, above is positive and below is negative, from left to right. Going from right to left, it's going to be the reverse. Okay, so after that, we're going to jump in and do just a bunch of integrals mostly. So 3, we just want to compute the integral of 3x squared minus 4x plus 2 dx. So this is just a polynomial, and remember, for a polynomial, that's all we have to do is add 1 to the power of x and then divide by that number. Unless it's a constant. If it's a constant, like the plus 2, we just stick an x onto it. So this is just going to be 3x to the third, and then we divide by that 3. Sorry, that's a minus, not a plus. And then minus 4x squared. And then we're going to divide by a 2. And then, as I said before, the 2 becomes a 2x. And when it's not a definite integral, meaning there's no limits with the integral symbol, we just add that plus c for the constant of integration, for the family of integrals, the most general integral. And then minus 2x squared plus 2x plus c. So I was just simplifying the things that could be simplified there. So pretty straightforward there. That's a polynomial. So basically the rule there is the integral of x to the n dx is x to the n plus 1 over n plus 1 plus a constant. This is for polynomials. You can't try and use this rule for other functions, right? The rules are very specific to which type of function you have. So for number 4 here, we're going to have the same sort of thing, but we're going to have different functions involved. So we want to compute an integral of, say, 3 to the x minus 5 divided by x dx. So we want to do each term separately, and this just requires a couple of rules. So for exponential functions, there's 2 rules. One for the standard form and one for the continuous form. And then for 5 over x, we just need to recognize that the antiderivative of 1 over x is the natural log of the absolute value of x. So these are just the other rules that we encounter. So this one just comes out to 3 to the x over the natural log of 3 minus 5 times the natural log of the absolute value of x plus our constant. Nothing to simplify there, so we're already done. So the integration rules here, there's 2 of them. So 1, the integral of, say, a to the x dx is a to the x divided by the natural log of a plus a constant, and then 2 the integral of 1 over x dx is the natural log of the absolute value of x plus c. So one other rule that we didn't use, the other one, so another one that we didn't use here, so let's call this 1 star. If it were the integral of, remember, e to the kx, where e is Euler's number, this is e to the kx divided by k plus c. So we did not use 1 star here. In number 3 or 4. But I just wanted to remind you about the rule. Okay, so let's move on to number 5. So we're going to jump into the average height and net change section. So suppose R of t equals 3.4 times e to the 0.17 t, measures thousands of bacteria in a colony, t hours after an experiment began. How much did the bacteria increase after the first 4 hours? Okay, so remember this is just looking for net change, so we just want to integrate the function over the time interval. So since we're looking at the point it began to the point 4 hours later, the limits of our integral should be 0 and 4. And once you figure that out, that's pretty much it. So the net change is given by the integral from 0 to 4 of the function 3.4 times e to the 0.17 t. So we're using t instead of x here, as is often the case when time is represented. So here we're going to use 1 star that we talked about above. So basically 3.4 times e to the 0.17 t divided by 0.17 is the antiderivative. This is a definite integral, so we don't need a plus c. We just need to plug in the numbers and subtract them. And it actually turns out that 3.4 divided by 0.17 is 20. So this is really 20e to the 0.17 t from 0 to 4. So this comes out to 20 e to the 0.17 times 4 minus 20 times e to the 0.17 times 0. And this, if we approximate, comes out to 19.48. And remember, this number is in thousands, so this is 1,000 bacteria. And that is it for number 5. For number 6, we're going to look at an average value. So suppose we have this function, and it's going to look a little bit messy just because it's from a real model, so the decimals are kind of small. So minus negative 0.017 t cubed plus 0.53 t squared minus 2.9t plus 65 is the temperature in degrees Fahrenheit, T hours after midnight. I think this problem is technically in Mexico City, if I remember correctly. So what we want to do is we want to find the average temp. From 8 a.m. to 6 p.m. Okay, so remember the average temp formula is just... Okay, well, there's one thing to note. Notice that T hours after midnight, it corresponds essentially to military time here. So 8 a.m. is just the normal thing that corresponds to T equals 8. But 6 p.m. is going to correspond to T equals 12 plus 6, which equals 18. So those are our two T values. And then from there, we can use that to get the average temperature. So the average temp, we're using the average value formula for the function. So remember, we do 1 over b minus a, which in this case is 1 over 18 minus 8. And then we integrate from 8 to 18. And then we plug in our function there, which is negative 0.017 t cubed plus 0.53 t squared minus 2.9 t plus 65 dt. So again, there's some decimals involved, so you may need to use your calculator, but in essence, it's just a polynomial. So we're just adding 1 to the power of t for each term and then dividing by that number. So we have 1/10 in front, and then we can do the antiderivative. So we're going to get negative 0.017 t to the fourth over 4 plus 0.53 t cubed over 3 minus 2.9 t squared over 2 plus 65 t, and we need to plug in the 8 and the 18. So I'll write down the numbers you get when you plug those into your calculator so that you can double check the calculation to make sure that you can type it in accurately, but I'm getting 1 over 10, and then I'll keep 3 decimal places so that I can round it to accurately, so 1284.372 minus 500.24, I wrote down 53 here. So this comes out to about 78.4 degrees Fahrenheit. So that is the average temperature for that problem. So again, we're still just integrating like we did for number 5, but we have to add that one additional step where we divide by the length of the interval to get the average height. Okay, and then the last 4, 7 and 8, are going to be integration by substitution, and 9 and 10 are going to be integration by parts. So for number 7, we have the integral of x times the quantity x squared minus 5, x squared minus 4 to the 5th. So for each of these, we just want to integrate. So this one's substitution. So again, we want to let u be the x squared minus 4. And then we want to compute du. So du is just 2x dx. And then solve for dx. So du over 2x is the value of dx. And then we can transform our integral. So our integral will become the integral of x. And then we have this x, we're going to replace the x squared minus 4 by u. So that will become u to the 5th. And then dx can be replaced by du over 2x. So the x's will cancel, and we're just going to be left with the integral of u to the 5th dx, which is the polynomial rule, so u to the 6th over 6th plus a constant. For these indefinite integrals, we need to switch back to x's. So this is really just, oh, you know what I did forget? I forgot about this 2. The 2 didn't go away. So that's u to the 5th over 2. And then when you divide by 6, 2 times 6 is 12. So this is u to the 6th over 12. So we replace u by x squared minus 4. So we get x squared minus 4 over 12. That x squared minus 4 is raised to the 6th power, and then plus a constant. And that's the substitution there. So just don't forget that that 2 doesn't cancel like I did. So that's the substitution. We'll get one more substitution with an exponential function. So 8, let's say we have the integral of x times e to the 4 minus x squared dx. So on this one, we want to let u be that exponent. So let u be 4 minus x squared. And so then du is going to be minus 2x dx. So du over minus 2x is the value of dx. So pretty similar substitution to the last one. We do just have a negative now involved. So this is going to become the integral of x times e to the u times du over minus 2x. So again, the x's will cancel, which is good. We're only going to be left with an integral involving u's. So that is the integral of e to the u over negative 2 du, which e to the u has only itself as its antiderivative because there's no other constant in the exponent. So this is e to the u over negative 2 plus c. And then we want to change u back to what it represented, which was 4 minus x squared over negative 2 plus our constant. So that's it for number 8 here. So the substitutions are pretty similar for both 7 and 8. Again, the antiderivative rule 1 star is what we were using there, but there was no constant in the exponent. So numbers 9 and 10 are going to be integration by parts, which is the last section from chapter 5. So we want to integrate 4x times e to the 2x dx. So a substitution won't work here because, say, if you let u be 2x, the derivative of that is just going to be 2, and when you solve, it's not going to cancel that x like we saw in the previous problem. So when you have things multiplied together and substitution doesn't work, we need to use integration by parts. So remember the integration by parts formula. So integration by parts says essentially we're doing, we have uv minus the integral of v du. And we need to pick a u and a dv. So this is essentially the formula we're using. So we want to let u here be 4x, and dv is going to be e to the 2x. So we're differentiating u. So du becomes 4 dx. And the antiderivative of dv is v, and that is going to be e to the 2x over 2. So that's the 1 star rule we saw up above. And then we just plug that into the formula. So we get 4x times e to the 2x divided by 2 minus the integral of v times du. So we're going to get 4 times e to the 2x over 2 dx. So then we end up with 2x e to the 2x minus the integral of 2e to the 2x, just simplifying things a bit. And then we're pretty much home free. 2x e to the 2x just stays the same. And then we're going to have to divide by 2 to get the antiderivative of e to the 2x over 2. And that's going to cancel with the 2 in front. So we just end up with e to the 2x plus our constant of integration. And that is the antiderivative for number 9. So 10 is going to be similar. One more integration by parts using the same formula we saw above. So this is the integral of x cubed natural log of x dx. So here we want to let u equal the natural log of x, because the derivative of a natural log of x is much simpler than its antiderivative. And dv is going to be x to the third. Jump the gun there, already trying to do the antiderivative. So du here is going to be 1 over x dx. And v is going to be x to the 4th over 4. And from there we just plug both things into the formula that we wrote down for number 9. So the integral is going to be u times v. So we get x to the 4th times the natural log of x divided by 4 minus the integral of v times du. So we have x to the 4th over 4 times 1 over x dx. So the first part stays the same to the very end, x to the 4th natural log of x over 4 minus the integral of x cubed over 4 dx. And then that's just a polynomial now. We just add 1 to the power, so it's going to become x to the 4th, and then divide by another factor of 4. So we end up with 16 in the denominator. So x to the 4th natural log of x over 4 minus x to the 4th over 16 plus our constant of integration. And that is it for this problem. So that's the last section in chapter 5. Again, the test is going to be just like this, 10 questions. You have 2 attempts for each of them and I think that's about it. So email me if you have any questions. Otherwise, this is Dr. Lennon signing off.